Now here is the most important limit. If the limit equals 0 over 0, called the indeterminate form, you have a removable discontinuity, so you are not done. Now, there's a little asterisk here, and I think I forgot to put what the asterisk refers to, but for those of you going on to calculus, when you are looking at limits in general, 0 over 0 does not always mean that you have a removable discontinuity. 0 over 0 is called the indeterminate form because you have yet to determine if a limit exists. It may exist, it may not exist. It depends on what kind of function you are using in your limit. However, for our purposes, since we're using a rational function, a polynomial divided by a polynomial in our limits, and that's all we're going to be dealing with, when we see 0 over 0, we know that we're going to be able to remove the discontinuity and find the limit. Just remember that that's not true for every type of function, and you're going to see other ways to interpret this in calculus. So how do we go about determining if we have a removable discontinuity and if the limit might exist for 0 over 0? Okay, so first of all, we have to determine if we have a 0 over 0. So we always start by substituting the number into the function. So we have -1, so we have here -1 cubed plus 3 times -1 squared plus 5 times -1 plus 3, all over -1 plus 1. Well, clearly the denominator equals 0. The numerator equals -1 plus 3, -2, -2, -1 plus 3 is +2. +2 minus 5 is -3, plus 3, 0. So we have 0 over 0. Because we have 0 over 0, we know that -1 is a 0 of the numerator and the denominator. So recall from our polynomial unit that if 0 or -1 is a 0 of the numerator, that means the numerator has a factor of x plus 1 just like the denominator does. So we can begin to factor the numerator. We know that one factor in the numerator is x plus 1. We also know that the other factor, whatever it is, has to be quadratic because this is x cubed. So x times an x squared is going to give me an x cubed. So this will not be something that you can just simply factor just by looking at it like you could if the numerator was a quadratic. We're going to have to use division to find the missing factor, either long division or synthetic division. Since some people prefer one and some people prefer the other, I'll show it both ways. Let me start with long division. So if I take the numerator x cubed plus 3x squared plus 5x plus 3 and divide it by the factor that we already know in the numerator, we'll get the factor that we don't know. So first of all, I'm going to multiply by x squared. X squared times x plus 1 gives me x cubed plus x squared. Subtract the whole thing and I end up with 2x squared. Bring down the 5x, then I will multiply this by 2x. 2x times x gives me 2x squared. 2x times 1 is 2x. Subtract the whole thing, then I would end up with 3x. Bring down the 3. Multiply x plus 1 times 3, I get 3x plus 3. Subtract that and I get 0. So this factor, this right here, is going to be x squared plus 2x plus 3. So here is the missing factor. Now, using synthetic division, recall that what goes in the box is the 0. So we put -1 in the box. We put the coefficients of our divisor, no, I guess that's called the dividend. I can't remember. I think the dividend. Anyway, the big polynomial, the x cubed polynomial, we'll put those in here. Bring down the 1. -1 times 1 is -1. Add. Bring -1 times 2 is -2. Add. -1 times 3 is -3. Add. Get 0. You should definitely get 0 for the remainder either way that you do this. This translates to x squared plus 2x plus 3. So there it is again. So this is what goes in here. Now, we're not done finding the limit. Now we're ready to find the limit. So now that we have factored the original polynomial, or the original rational function that is in this limit, we can rewrite this now as x plus 1 times x squared plus 2x plus 3 in the numerator over x plus 1 in the denominator. This allows me to remove the discontinuity, remove the thing that makes the denominator and the numerator equal 0 so that I can actually find the limit. So now I'm going to take the limit of what's left over, x squared plus 2x plus 3, which means I'm going to substitute negative 1 into the function, negative 1 squared plus 2 times negative 1 plus 3, which gives me 1 minus 2 plus 3, which equals 2, and that's what we see in the spreadsheet. And I guess I forgot to show the spreadsheet earlier, but this is a good time to talk about it. So if we pick values that are close to negative 1, on the left we starting with x equal negative 0.5, and on the right x equals positive, or x equals negative 1.5. So we're approaching negative 1 from either side. So we're at negative 1.5 over here and negative 0.5 over here, and we're approaching negative 1. Notice what happens to y. Y doesn't get really big like it did in my previous example. Y gets closer and closer and closer to 2, both sides. Now notice when we get down to negative 1, when we put negative 1 in for x into this function, we get an undefined number. You cannot divide by 0. So this is saying error. You can't divide by 0. So notice, though, that we do have a limit. That's the interesting thing about here. We do have a limit. So this is a case where we have a hole in the grass. Now, actually, I'm going to draw this a little differently. So we have this place where when x is negative 1, y is 2, and we have values getting close to negative 1 in the x direction, and values getting close to y or close to 2 in the y direction, but exactly at that point nothing exists. So this is still a limit. We can still say the limit as x approaches 1 is 2. In other words, x getting close to 1 means that y is getting close to 2, even though the point negative 1, sorry, there should be a negative 1, even though the point negative 1, 2 does not exist. So we do have a limit here. This is the limit that is going to be crucially important for what we do with derivatives as we introduce that calculus topic.